acids donate one hydrogen ion to a base. But what happens if you have more than one hydrogen in the structure? Can acids donate more than one hydrogen ion? And the answer is yes. And we talk about mono, di, tri, and polyprotic acids, depending on how many hydrogen ions are able to donate. So if you have a monoprotic acid, then a monoprotic acid can only donate one hydrogen ion in an acid-base reaction to whatever base is reacting with. So a typical example of a monoprotic acid is hydrogen chloride. Hydrogen chloride has only one hydrogen. So when it reacts with water and it donates the hydrogen to the water, it liberates the chloride anion, and the hydrogen ion goes to the water to generate this species H3O+, which is also called hydrogen ion, and we'll talk about why it's called like that in a few slides. After that, there are no more hydrogen ions, so this chloride anion cannot continue reacting, and the reaction stops there. When you have a diprotic acid, and an example of a diprotic acid could be, for example, carbonic acid, H2CO3. Well, carbonic acid has two hydrogen ions, so it can donate those two hydrogen ions to whatever base is reacting with. Let's use water again as our example. And you can write equations that show you how that transfer, how that donation goes. So if I think of my carbonic acid, H2CO3, reacting with one molecule of water, then if it donates one hydrogen ion, this species H+, what do I have behind? Well, I've got HCO3. CO3 hasn't changed, the hydrogen, you have lost one hydrogen, and because the hydrogen has gone away without the electrons, as a H+, it has left the electron behind, you get a negative charge. That's called the hydrogen carbonate anion, or you might be more familiar with the common name bicarbonate anion. Where has the hydrogen gone? Well, it has gone to the water. Water has behaved as a base, accepting the hydrogen ion. So instead of H2O, now you have H3O, and you've got plus because it hasn't accepted a hydrogen. It has accepted a hydrogen ion, a hydrogen with a positive charge. In the previous case, when you made the chloride anion, the reaction stopped there because that was it. There were no more hydrogens to donate. However, in the case of the hydrogen carbonate anion, there is another hydrogen there. So you could see another hydrogen being donated to the water. So you would start with the species you have made, the species hydrogen carbonate. It will react with another molecule of water, so a different one, and it will donate the hydrogen ion to the water. It leaves the electrons behind, so now there's no more hydrogen, and you get two negative charges. One you already had from the previous reaction, another one from the loss of this second hydrogen ion. And where that has hydrogen ion gone? Well, it has gone again to the water to make another H3O+. So as you can see, when your acid has more than one hydrogen that can be donated as hydrogen ion, it will donate them more or less easily. We can discuss this, we will discuss this in a future slide, but it can, it can donate them, and it will, to a different molecule of water each time. So as you can see, I've established the reaction, one hydrogen ion at the time, and with a different molecule of water. So it's important that you keep that in mind. You can also have a triprotic. That means that you have three hydrogen ions that can be donated, or a polyprotic acid. I mean, you have 4, 6, whatever. Inorganic acids, they stop at 3 hydrogen ions, but when you have organic acids, and I can give you some examples if you're interested, then you can donate quite a few extra hydrogen ions. So I'm going to ask you to stop the video now and have a go at proposing the reactions of this compound, phosphoric acid, with water. how would these equations look like when it transfer one, the first, the second, and the third hydrogen ions to 3 different molecules of water? Stop the video now, please. So how would I go about doing this exercise? Okay, phosphoric acid, H3PO4, donates one hydrogen ion to the water. That means that it ends up being H2PO4 minus, because we are donating this slightly mythical species called H+. That hydrogen ion has gone to the water that is behaving as a base and accepting that hydrogen ion, so you end up with H3O+, because you're accepting an H hydrogen with a positive charge. Because this species is called dihydrogen phosphate, this H2PO4 minus is called dihydrogen phosphate. It still has hydrogens, so it could still continue reacting with other molecules of water. So I can set up a second equation that would explain how it loses another hydrogen ion. You've got the compound H2PO4 minus, the anion. It reacts with another molecule of water. And again, it donates the hydrogen ion to that molecule of water, so it loses a further hydrogen, PO4. It has already a negative charge from the previous that it was already bringing here, and now it gains another negative charge from having donated this H+ to the water, so it ends up with 2 negative charges, HPO4 2 minus, and that is called the hydrogen phosphate anion. And again, as in the previous case, you produce H3O+. And that would be a second equation, the loss of the second hydrogen ion. The compound HPO4 2 minus, the compound hydrogen phosphate, still has hydrogen, so it could still continue reacting with water, with another molecule of water, and donate another hydrogen. HPO4 2 minus will react with another molecule of water, and it will donate that H+, that hydrogen ion, so it would generate PO4, phosphate anion, and it would get 3 negative charges, 2 that it already had, and an extra one from the loss of this final H+ hydrogen ion. And it will generate another H3O+ ion. And here the reaction stops because the phosphate anion does not have any further hydrogens, so it cannot continue behaving as an acid. And that's what we call it a triprotic acid, because it donates it has the capacity of donating 3 hydrogen ions to 3 different water molecules.